Electric and gravitational fields. Earlier, the similarity between the electric force and the gravitational force was noted. There's a similar relationship between the electric field and the gravitational field because they both generate central forces. Central forces are directed in a straight line to or from an object from a point in space. The magnitude of the force depends on the distance between the point and the object. There is a key difference between the two fields and forces. Mass, which is the source of the gravitational field, is always positive, and the force is always attractive. The gravitational field always points towards the mass generating it. Charge, the source of the electric field, can be negative or positive, and the force is either attractive or repulsive. The direction of the electric field points away from a positive charge and towards a negative charge. Given that a mass m is located at the surface of the planet with a mass of big M and radius r, so we have a planet with a radius capital R, the planet has a mass of m, and we have our second object right on the surface, and that's little m. Newton's law of universal gravitation is used to determine the magnitude of the gravitational force between the planet and the mass. So we can use this right here. Divide this expression by little m, and we're making the assumption that little m is much, much smaller than big M, the mass of the planet, and we get G, the gravitational field. So you just take the gravitational force, divide it by the small mass, and we get an equation for the gravitational field created by that planet. The weight of an object on a planet, or the measure of the force between the object and the planet, is expressed by this equation. The force due to gravity is m times g. So you just take g here, if you multiply it by m, you'll see that you end up with the force of gravity, and that gives you the weight of the object. The mass of the object remains the same wherever it is, but its weight is dependent on the gravitational attraction g of its surroundings. Here is a comparison chart. So for gravity, we have Newton's law of universal gravitation, Gmm over r squared. For the electric force, we have Coulomb's law, kQq over r squared. So very similar equations. However, the constant in Newton's law of universal gravitation is a really small number, whereas the constant in Coulomb's law is a really big number. Gravity and the force of gravity and the gravitational field all depend on mass, while the electric force depends on charge. They both depend on r with an inverse square relation, so they both have r squared in the denominator. And gravitational field and electric field equations also look really similar. So to get the gravitational field equation, you just divide the force of gravity by m. To get the electric field equation, you just divide the force of the electric force by little q. So those go away, and we are left with the equations for the field due to one of the objects.